All right, so let me clean up these news articles. A beacon is a little image they put on an email to see if you read it, and they put them on web pages too. So they're like cookies. They identify you. Tomorrow, there's a guest lecture in my Thursday night class. This is worth extra credit if you go to it. You can tune in on Zoom. I'll also be here physically in the room if people want to, like an SLA. I don't know what SLA is. Yeah. Anyway, so I have no lecture in my Thursday class. I'll be around to answer questions afterwards, but if you tune into this, it's worth extra credit. I just mentioned that. All right, so let's talk about encryption. And that's here, 141. Good evening. We're down to 5 stream ciphers. All right, and this is 141. All right. There we go. All right, and before I start talking about the stream ciphers themselves, I want to add a little bit to what we said about block ciphers last time. So the first few slides here are just adding something that was a very common topic of discussion about block ciphers. A service link announcement. Yeah, mobile, I don't know what that is. I've never noticed them. Yeah, I was thinking of the Symbionese Liberation Army too, but anyway. All right, so this video has a teacher teaching a class explaining what happened with the NSA hacking into DES. And what he says is the NSA first weakened DES. The Lucifer system that they got from IBM, deciding on the United States' first government-approved symmetric cryptography system, had a 64-bit key. And the NSA said, we can shorten that to 48. And people wouldn't go for it, so they compromised to 56 as the shortened key. So they weakened it against brute force attacks. And this was in the 70s or 80s, a long time ago. And then the NSA strengthened it, however, because the NSA had a classified cryptographic attack, which the people in the non-military sector did not know about, called Differential Cryptanalysis. It's a chosen plaintext attack where you send in plaintext and then you change the plaintext just a little bit, like 1 bit, and encrypt it again, and you compare those 2 encryptions. And from that you can deduce something about the cryptographic scheme and the key. And nobody knew about that technique except the NSA, and the NSA improved the Lucifer system to resist that attack. So a decade or more later, when that attack was known, people went and analyzed it, and they said you had to use the particular parameters in the S box, which we saw in AES. It's this box where you look things up to scramble the data, and they wouldn't explain where they got those values, but it turned out eventually those values were carefully chosen to resist this attack. So what they were doing here would seem confusing to people. If they wanted to make it as secure as possible, they would leave it at a 64-bit key, or indeed examine it and raise it to 128, and strengthen it against the S box. But what they were doing here was achieving this no bus. They wanted to weaken it so the NSA could perform a brute force attack. So they wanted less possible keys, but they wanted it to be strong enough that nobody else could get in. So they wanted it just strong enough that they could get in with their very powerful military computers, but they believe nobody else has computers that powerful, which might have been true in the 80s when this thing was designed and used. This is what the NSA tries to achieve, is no bus. They do not want the strongest encryption. They want just the right level of encryption to lock out everybody else except them. The problem is this always depends on there being a secret. They have their military secrets to get in if they have some kind of secret backdoor. Now this one was sort of a brute force backdoor, so it was clearly going to be temporary. As computers improved, other people will eventually be able to do the brute force attack, and that's what happened. But the problem is many of them involve them keeping a secret, like the way they tried to poison electric curve cryptography, version of it. They were accused, although they haven't admitted it, of carefully choosing parameters that they knew to generate the key so they could decrypt the data, but nobody else could ever find those parameters. So now it just depends on them holding a secret, like a secret backdoor key. And the problem is, of course, Edward Snowden leaked out a ton of secrets in 2013. So that makes you think the NSA doesn't keep their secrets very well. And then in 2017, WannaCry hit a ransomware, which was again based on NSA's secret exploits, which again were stolen by the shadow brokers, and people still aren't sure who the shadow brokers are. Some people say it was another NSA insider, like Snowden leaking them. Other people say it was the Russians hacking in. But anyway, both of those pretty clearly demonstrate that the NSA is not, in fact, very good at keeping secrets. And therefore, that kind of fouls up the whole concept of no bus. But they continue with that because their mission is to find all the confidential data in the world and make it available for the American government to examine. So it is their duty to hack into everything, and that's what they're doing. Anyway, let's go on with stream ciphers. So we'll talk about how they work, the difference between hardware and software oriented, and what can go wrong. So a stream cipher, now block ciphers and stream ciphers are symmetric. Both of these are the classic kind where you have a secret key and the other person at the other end has the same secret key. So you have to somehow deliver that secret key over a secure channel. Doesn't solve that problem. Now block ciphers work on blocks of ciphertext, typically 16 bytes. So you have to fill it with padding, fill up the 16 bytes, and you encrypt each byte like AES. Stream ciphers use the key to produce a pseudo-random stream of bits, just a long stream of apparently random bits. Then you just XOR the stream with the plaintext, so you don't have to pad anything. Your plaintext can be any length. You're not required to use a whole block of key stream. You can just use as much stream as you want. So that's nice. And so one way to do it is with a deterministic random bit generator. You just feed in a seed. This is how the random number generators work in like Python and C. You feed it a seed, often you use the clock time or something, and after that you call it over and over and it gives you a series of random numbers, and they're completely deterministic. If you feed it in the same seed again, you'll get the same series of numbers. So that is essentially what all of these are. All right, and so they typically use a key and a nonce. The key is the secret, because once you've delivered the secret to the person at the other end, you don't want to have to keep giving them a new secret for every message. That would never work because, the secured link is hard to set up. So you use the same key for many messages and you change a nonce for each message. The nonce is not secret. You transmit that in the plaintext. But the nonce has an effect on the encrypted message that depends on the key and cannot be deduced easily from the key. That's the idea. So now you feed in the key and the nonce into the stream cipher. That creates a key stream of pseudo-random bits, and you just XOR those bits with the plaintext to make the ciphertext. And at the other end, they just do exactly the same thing because the second XOR gets you back to the plaintext. So that works. What's that?
Wouldn't your deterministic random generator kind of like, screw up everything deterministic?
No, that's essentially what this is, right? That's essentially what this is, a deterministic random generator. You take your key and somehow you create a series of bits which can be reproduced at the other end. Now, the only thing wrong with this one is it uses a seed, and you need to have a key and a nonce. So you can do a series of messages. But that's essentially what's going on here. Your stream cipher is essentially a pseudo-random bit generator that depends on both the key and the nonce.
What I'm saying is your random number generation is deterministic.
Yes.
And your key and your nonce is open.
What's open?
The nonce.
The nonce is open, that's right, but not the key.
Okay.
And you can only create, that's right, so the nonce is not a secret, but the key is a secret. And the nonce alone is not enough to determine the bits. That's important. Good? All right. So that's the point. You take the nonce, which is not secret, combine it with the secret key, and then you create a pseudo-random bit stream, key stream, and you XOR that to encrypt, and you XOR it to decrypt. So the person at the other end that has the key can take the nonce and the plaintext that are sent through an insecure channel, and a nonce and the ciphertext, and reverse it back to the plaintext.
So your key is kind of like a seed.
Yes. Yeah, the key and the nonce essentially work together like a seed. Yeah, exactly. All right. Now, so one thing that can happen as a mistake is you can use the nonce twice. If you do, then those two messages are based on the same key stream. So if you XOR the two messages together, any region in one message that's all zeros will become plaintext in the others. And this mistake has been made many times. Russia made this mistake. We talked about it in the two-time pad. And Microsoft made this mistake in Microsoft Office encryption. They had password encryption of files using a key generated from a password, and there was no nonce. So if you encrypted two Microsoft Office documents with the same password, you could just XOR them together, and whole regions of it would become clear. It's a common mistake. And of course, that's what we talked about last time. The two-time pad works this way. Even if you have a perfectly random bit stream, if you use it twice, you can break in, because you have two messages that are too simply related. Okay. All right. Anyway, so there's stateful and counter-based stream ciphers, two ways to do it. The stateful ciphers have an internal state that keeps changing with a series of iterated calculations, and the counter-based block cipher has a counter instead of a safe. And this is very much like the different versions of AES. So here's the state cipher. You have an initial state, you feed in the key and the nonce and do a calculation, then you update it to change the state, and update it again to change the state, and update it again to change the state. So this is a little bit like cipher block chaining. You have to do them all in order. You have to do this one before you can do that one. And then you have a key stream coming out here, blocks of key stream, and you just XOR it with the data. So this is one way to do it. You have this internal state that you keep changing. The other way to do it is where you just use a counter. So you take a counter value here, in addition to the key and the nonce to create a block of text, then you take the next counter value and the next counter value. And you could just have the counter counting up, but these days they prefer to use something called the Galois function to create a series of numbers. But anyway, it's deterministic. And so it's just another way to create blocks, but this way the blocks don't depend on the previous blocks. And they both amount to about the same thing. Then the counter means that replaces the state. Instead of having different blocks working on the previous block, you just add a different counter, which changes the bits.
And the P is your data going in?
Yeah, the P is your plain text and the C is your ciphertext, yeah. So you do this and get a block of key stream, you XOR the plain text to get the ciphertext, and then you just make another block and another block until you have got enough bits to encrypt all your data. And even though they're created in blocks, you don't need to use a full block. If you only have one bit you want to encrypt, you can just use the first bit of the key stream, so you don't have to pad anything the way you would with AES. AES in cipher block chaining mode. All right. So now you can talk about how you're going to do this. It was originally intended to go in hardware. The original DES was designed because the computers were a lot slower and they wanted to build hardware devices. So application-specific integrated circuits are the fastest kind of hardware, where you make silicon specifically designed to do just one calculation. That's the best, but it only works, of course, if you have some calculation that is really important and popular and you can sell, thousands or millions of chips. Programmable logic devices and field programmable gate arrays are slower, but ways to do this where you can program the hardware to be almost as good as specialized hardware. So the software implementations, of course, are using microprocessor instructions, things like add and sub and multiply and divide. It's going to take words, typically 32 or 64 bits. The hardware will just work with bits. You have parallel lines, bit by bit, runs right through. So the first stream ciphers required less memory and logic gates than block ciphers. So it was easier to make hardware to implement a stream cipher than it was to make a block cipher. So by quite a large amount, 1,000 versus 10,000. So they were popular. Now DES was optimized for hardware. And at this time, the target applications were hardware implementations using S boxes, fast in hardware but inefficient in software. AES is more efficient in software. And the modern world is typically done in software.
What are the S boxes?
The S box is just a box you look things up in. We saw it last time in the AES. In fact, let me bring it up because that's easy enough to see. That would be chapter 4. Let's bring it up because other people may very well have the same question. The S box was here, and I'll get to it. We get down here. Okay. Round key. Yeah. I think it's in this video. Let me play the video from 4A because that's where it is. It isn't in the slides. There it is. It's in here. Yep, substitute bytes. That's what uses the S box, and we're going to see it in a minute. That's it. That little thing is the S box. So what you do is you take 1, 9, and you look up 1 this way and 9 that way and just replace it with this number. It's just a lookup table that takes every byte and turns it into another byte. And how you construct this is not obvious at all. You'd want it to be sort of random, and this is what the NSA did. They made the S box so it resisted differential cryptanalysis when that was not even a known attack. And so that's complicated, exactly how you choose to scramble it. But that's a way to scramble the data. And it's,
Like a one-time pad,
what's that?
kind of like a one-time pad.
Well, it's not a one-time pad because you use it over and over. You use the same box to encrypt every byte.
It's like kind of like, just like a lookup thing.
Yeah, it's a lookup thing, and I think you have to have all different bytes in here too. They're not really random. It's just shuffling them all. But it's just a way of altering it. It turns out to be an important yeah, there's no sound in that video. An important part of the encryption process. That's the S box, a substitution box. Good? All right. So ASIC is the fastest, but costs thousands of dollars. Here's how they work for cryptocurrency mining, which is currently a way to measure how good they are. These are 100 times faster than a CPU. GPUs are cheaper, but not as fast. CPUs are very slow. You can't, and so this is how it was mining Bitcoin a couple of years ago, which is, a good way to test how fast hardware is. ASICs are the fastest. Special chips designed just to do this one thing, of course. So now let's talk about shift register. This is one way to get a series of bits. So you can start with some bits, and then you can just shift it to the left over and over, and one bit that falls off the end, you call that the output. So if you have 8 ones and shift it to the left, you'll get 1, 1, 1, 1 as you go shifting it over, and then it will all be zeros after that. So that's a shift register, which is not doing much, but we'll move forward from that. So if you start with a different value, like this, 170, then you would get alternating 1, 0, 1, 0, 1, 0, and after you had 8 of them, you'd all be gone and you get nothing but zeros. So that's a shift. Now, a feedback shift register doesn't run out after just 8 bits. What you do is you shift it to the left, and then you fill in the bit on the right with a bit that's calculated with some function from the existing data. And so you have some way of combining the bits to calculate the new bit. So here is a combination where what you do is you XOR all the bits. So that means if you have an even number of ones, the answer is 0. And if you have an odd number of ones, the answer is 1. So here you have 4 bits. Okay, then you calculate, you shift it to the left, a 1 comes out, and the new number you add on the right is 0. Now a 1 comes out, and the new number you add on the right is 1. A 0 comes out, the new number you add is 1, and so on. So this way, the bits keep renewing, so you have a stream of bits, but they're not really that random. I mean, with 4 bits, you could have 16 possible values. But in fact, it's 1, 2, 3, 4, 5, and then you get back to the first value. So you really only get 5 different values, not all possible 16, before it repeats. And in fact, here's what happens. There are 3 loops of 5, and 0 is alone. Because 0, the new bits you fill in are always 0, and so you never get anything but zeros. So that's how this feedback shift register works. It does not give you the maximum number of different values. So that's a problem. All right, and so we saw this at a period of 5. Now, in principle, you could have a feedback shift register that gave you 2 to the n minus 1, because 0 is always going to be all zeros. So that one's no good, but all the others could be in a big loop, so you get more. That would be the best possible linear feedback shift register. And here's another one where you only XOR 3 of the bytes, 1, 3, and 4, skipping 1. This turns out to be a lot better. If you do it, this one has a period of 6. So it's a little better than the ones with a period of 5, but still not perfect. Same sound back? Yeah. Did you say you couldn't hear me for a while? You just couldn't hear the video. That's rude. If you're losing my voice, let me know. Let's see. Let me check on this. Can you hear me talk? Well, hopefully will be a reply before. Sound was good throughout. Okay, good. So some people can hear me. Okay, good. Thank you. Okay. Well, it may have been, oh, yeah, the video didn't have any sound. That's okay. Good. Okay. All right. But I just checked because, if few people can't hear me, then I need to know that. All right. So here's one with the maximal period. So now you just XOR 2 of the bits. And this one, all right, the same kind of thing. And this one actually has the maximal period. You XOR these 2, and you fill them with a 0. You XOR these 2 and fill them with a 0. Now it's a 1. Now it's next one's going to be a 1, next one's going to be a 0. This turns out to have a maximal period. You see it's 4 times 4. It takes 16 calculations to get back where you started, so it has the maximal period. It gives you all 15 possible values except all zeros. It's the only one you never see. So that's the best you can have with a linear feedback shift register. Now the problem is, if it has n bits, the attacker only needs n output bits to recover the initial state. All you need is one group of 4, and you can totally recover the initial state and predict all the bits. And that's because you're effectively solving for some linear equations. So the linear feedback shift register is not very good. We're going to improve it. So one thing you can do is have a linear feedback shift register and then have a calculation to create the output that is nonlinear. So you don't change the functionality inside here, but you change how you calculate the output bit by mixing and XOR, which counts to what they call a nonlinear transformation. So this sort of disguises the internal workings, and that makes it better, but there are still some attacks, algebraic attacks, cube attacks, and correlation attacks, because you haven't really changed the fact that the underlying operation is very simple. You've just disguised it with the output. So what's better is a nonlinear feedback shift register, where you make a nonlinear function mixing and XOR together and combining these in a complicated way. That makes it very difficult to analyze or attack. Nobody can predict the period exactly or even know if it's maximal, but it's much harder to attack. And so in practice, the way to make a good bit stream is to combine the two. You have a nonlinear feedback shift register and you have a linear feedback shift register, and you combine them together to make the output. And now you can make sure that this one has a maximal length so it won't repeat, and you can make sure this one is hard to attack so it's hard to attack, and that turns out to be the sweet spot. And the recommended shift register is this thing called Grain 128A, which is considered to be the best currently available. It takes a 128-bit key and a 96-bit nonce, and off it goes. And the linear feedback function is this strange thing, just picking various bits out of the 128 bits. And the nonlinear feedback function is this bizarre mess, combining XOR and AND operations in a complicated way. And that seems to result in what's currently considered the best combined feedback shift register. It's proposed in 2006 and improved in 2011, and it's considered very good. It's not very commonly known, though. Apparently it's only used in proprietary industrial systems, but it is considered a very good pseudo-random bit generator.
What is the AES used?
What is what?
What is AES used?
ADS?
AES.
Is it on this slide? What?
No, this one.
ADS, you say?
This is talking about Ciphers, you said, right?
Yeah, feedback shift. Yeah, linear feedback shift register and nonlinear feedback shift register.
AES encryption is not using this.
Oh, AES does not do this at all. AES uses different transformations, like an S box, shifting bits. We did it last time. AES does not use this system at all.
It does not use this.
No, AES does not do this. This is just a feedback shift register.
Is this just experimental thing?
No, it's in current use. It's not just experimental. It's currently used in some hardware.
So it's not in a standard.
It's not in any of the cryptographic standards we're using normally. See, it's not that popular, but it is a shift register, a way to create pseudo-random bits.
Yeah, this is not more like secure.
Well, it serves a different purpose. This is just a source of random bits. It's not yet an encryption scheme. Right. But see, you could use this you can be used as a stream cipher, and it is used in some proprietary implementations, but it's not used in AES or anything common.
Not in the standard one.
It's not in one of the standards that we commonly use. So here's stream. Now, this is what was used in telephones. In a 2G, they used this thing called A5/1, and it turned out to be pretty weak. And there was A5.2, which was one of those weakened export versions, deliberately crackable, which was a big thing that the US government did in like the 1990s. A5.1 was leaked and reverse engineered in 99, and it has serious security weaknesses. The NSA can routinely decrypt it. A5.1 has 3 linear feedback shift registers. That's how it works. 19 bits in one, 22 in another, and 23 in another. And it uses complicated functions to update them. And in order to make it more secure than a simple linear feedback register, it does not rotate them all every time. It only rotates, it has a rule, the clocking bits. it takes certain bits to decide which one of them to move, so they don't all move together. So it's a little more complicated than just one linear feedback shift register. But the problem is, it turns out, because you broke it up into these chunks, you attack it with something like the meet in the middle attack. You can attack just one part of it at a time, and then the brute force attack becomes possible. So the brute force attack, if you were to try all 64-bit keys, that would be 2 to the 64 operations, and that's really a lot. Although it could be done now, it certainly could have been done decades ago when they made this system. But there's a faster attack where you exploit the fact that it's a short key. You brute force the internal states, 2 to 19 for the first one, 2 to 22 for the next one, 2 to 11 for the next one. So you guess them separately and make 3 tables and then mash them up like the meet in the middle. So that's the problem. The fact that you can break it up into smaller problems means you can crack them and you have a much faster solution. So this turns out to be completely crackable. And so another way you can do it is with time memory trade-off. Now you cannot make a lookup table of 2 to the 64, but you can make a lookup table with a lot of it. You can't do all 2 to the 64 possible keys, that would be too much memory, but you can do a smaller lookup table with part of it and trade memory for time, and they were able to do that in 2010 with a 2 terabyte table. They were able to use GPUs and decrypt it in near real time. I remember hearing about this at DEF CON, and I was amazed. I saw they said, we made a system that can just decrypt encrypted phone calls on the fly by looking them up in a 64-bit table. And all I did was I thought of this at the time, and I said, that's not possible. But that isn't what they did. They found a smart way to do that another way without requiring all that memory. So that 64-bit encryption was not good enough. And so that's obsolete now. It's been abandoned. It's not using the 3G or 4G networks. This is using the Kasumi block cipher, which some people are concerned the NSA has a backdoor in, although I haven't heard of anybody proving that. And I don't really know what 4G and 5G use. It might be the same. Anyway, those are stream ciphers, the first bit. So let's take a look at a Kahoot. (141.5a). Going in, I ought to turn on the lights. Oh boy. Someone's getting into Halloween a little bit early. All right. I'll give it a few more seconds. All right. All right. So what Cipher uses init and update functions. Yeah, that's the stateful one, which works, like a hash function. You update it and update it, update it, the state, changing the state to the next state. That's how you create blocks of key bits, key stream. All right, which one was designed in the 70s for hardware? DES, good. All right, which system do you break into with Burley Camp Massey? Not sure I spelled that right, but anyway. Yep, that's the linear feedback shift register. That's a system of using n values that come out to predict the internal state. All right. Which one uses an LFSR and an NFSR? That's Grain 128A, which is probably the best stream cipher. Unfortunately, it's not the standard anybody's using for much of anything, which is fairly common. You know, like we say, there's often a good one, but some earlier one has become the standard. AES is a block cipher, right? And so this is skulls. They'll have to tell me who they are for that point. But the other two, I know who they are. All right. The stream cipher does have a key, and so Grain 128 has a 128-bit key and a nonce. You have to have a key side. It does have a key. So if you go back here, they all use a key. Like, you know, A51 had a 64-bit key and a 24-bit nonce, and Grain 128 has a 128-bit key and a 96-bit nonce. So they all have to have a key, just like AES, but they're a stream cipher.
So they have like a 128 blocks of thing?
No, it takes those 128 bits and it uses them like this. It puts some of them here and some of them there.
Yeah, so that's why they have 128 blocks of this thing.
Yeah. Well, no, all 128 bits go in here. Like if we go to the earlier one, you can see it. The one with the 64-bit key, you'd use the 64-bit key here. Yeah, 19 bits of it went here, 22 bits and 23 bits here. So you just had one block, and one block, and that's all. It uses, and this one here uses, out of its 128 bits, it uses some of them here and some of them there. So doesn't have 128 copies of this diagram. One copy of the diagram is the whole thing. And the key bits go in here and the nonce bits go in there. And then you just run the machine. And out come an endless stream of pseudo-random bits down here. That's important. You don't need 128 copies of this diagram. One copy is all you need. And these things are something like 128 bits wide. Good. Well, I see somebody's got a question here. Which cipher is used in Use 5G? Oh, good. Did we get an answer? Let's see. It's a good question. I don't know the answer. Let's see. I think the stream cipher Snow and AES. Well, I don't know. 4G are reused. Okay. And Snow 3G, AES counter, and Zuck. Well, okay. Sounds like stuff that's not covered in our book, but that's interesting. That may well be true. I'll put that in my news links.
So it's a 16 stage.
What's that?
So it's 16 stage.
16 stage, you say?
Linear.
Yeah, 16 stage linear feedback shift registers. Yeah, with each stage this. Yeah, that's true. A 16-stage linear feedback shift register and a, word-based, whatever that is. Yeah, they're all stream ciphers. That's interesting. Good point, and he has papers to look them up, so good. I'm glad you people are looking up good stuff. All right, so anyway, we were at the first Kahoot. Good. All right, so now let's talk about the software-oriented stream ciphers. So these are intended to work on words, 32 or 64 bits at a time, because that's, of course, the way CPUs work. So stream ciphers, in fact, have become more popular than block ciphers because of the padding oracles, although switching to counter mode in the block ciphers has improved this. Our cryptographic standards have gone from block ciphers to stream ciphers and back to block ciphers, back and forth as various flaws are found. RC4 was the super popular stream cipher, built into almost everything for decades. Basically ubiquitous, used in WEP and TLS and many, many other systems. It was very simple and very popular, and it turned out to be very insecure, but it took people a long time to find that out. And they finally abandoned it around 2515, is when everybody tried removing it from all the systems. But it's very simple. It was invented by Ron Rivest, and it works like this. You have 256 bytes for the internal state, and you start them with just 256 numbers in order. And then all it does is shuffle them like a deck of cards. You don't use XOR or AND or anything like that. All you do is you have a key, you have an n byte key, which is the K here, and all you do is for each one, you go 256 times, you've swapped two cards, and you choose the two cards you're going to swap with a very simple calculation. You have a counter J, and you have a counter I, and you take J plus the state of I plus the key of I modulus N, and that's your next J. So you flip that card, slash I and SJ, and then you do it again. So you just flip two cards, you flip two cards again, you flip two cards again, you flip two cards again, and you do that 256 times, and then the internal state is all scrambled. And therefore, you can take some part of that to be the output to create your key stream. And so it's very fast, very simple, doesn't use any of the feedback shift registers or anything. Yeah, somewhere, they don't tell you what part of this you call your data. I guess you take a block, like the first block, and call that the output. After you do this, the first block is effectively random. You take that, and then you do it again and again.
The S is the input, right?
The S is the state. The input is the key. So the key is here, which can be as long as you want, N, and the S is the internal state. It just starts with all these numbers in order, and then for 256 times, you swap two of them.
S is state, so what's your input?
The only input is the key. Remember, this is a stream cipher. So you put in a key, and out you get a stream of bits.
Don't you need the data?
No, the data, all this does is create the key stream, and then you XOR it with the plain text to get the data. So you don't feed in all you do is feed in the key. That's the game. And this turned out to be fast and easy, and people thought it was good, but it had a lot of flaws. So then you encode your plain text P, you just generates m bytes of key stream. Here's the key stream. Yeah, you get the key stream here by combining those 2 bytes. Some of these bytes. So I guess this is how you do it. You run it only for m, so you only flop them, and somehow you combine them here. This creates a pseudo-random series of bytes, but it turns out to have serious flaws. Now here's one problem. There's no nonce. All there is a key. So if you want to encode a second stream of data with the same pre-shared key, you have a problem. So in WEP, what they did was they just treated the first 24 bits of the key as a nonce. So that means you'd be using a different key every time you change the first 24 bits, but you'd send that in plain text. So that was not a very good, if you're going to have a nonce, you want to use a crypto system that is designed to have a nonce. You can't just pretend that part of the key is part of the nonce, because then you're revealing part of something that was supposed to be secret. And there's 2 problems. In the first place, a nonce is too short. If you have a 24-bit nonce, that means after 2 to the 12 packets, you'll have a nonce collision. And therefore, that was some of the early attacks on WEP just involved catching enough frames that you get 2 packets with the same nonce. The nonce is sent in the clear, and then you know they're encrypted with exactly the same key stream. So that's one flaw. But there are much worse flaws. All right, but if you know the nonce, then you know by the way, if you know the nonce, you know the first 3 bytes of the key, because you used it the first 3 bytes of the key, so that opens the door to deducing more. And also, in wireless networks, a whole bunch of the packets are all almost exactly the same. All the ARP packets are easy to spot because they're small, and they're all almost identical. They have only a few bits changing, so it gives you another real easy way to attack it. So WEP was ratified in 99, but the attacks started appearing in 2001, and just an endless series of more and more powerful attacks came out until everybody abandoned WEP entirely. TLS doesn't add a nonce. It uses a unique 128-bit session key, and it can change it for every message because it has public key encryption to send the key. But the problem is now there's another flaw, which is really serious. The key stream byte is not white. It's not random. The first byte is 0 twice as often as it should be. It should only be 0 one time in 256, but it's 0 1/128th of the time. And it turns out that many of the first bytes have a high probability to be 0. And what that means is there are serious exploits. All of the first 256 bytes have a higher probability being 0 than anything else. And remember, you're just XORing this with the plain text. And when you XOR something with 0, it does not change. So this opens the door to an unbelievably simple attack. All you have to do is get the same plain text to be encrypted millions of times, and the most likely ciphertext is equal to the plain text, block by block. So you don't need to know the key at all. You just need to find the most common value, and that is the plain text. So that's a really serious flaw. Of course, that will only happen if you can get like 1 million of the same plain text encrypted with the same key, but there were a whole series of attacks that did this on TLS. They would use JavaScript or something to just keep feeding data up to the server over and over again, making a new session, and then they could, you don't need to know the key, you don't need to reverse the encryption, you just need to find the most popular value, and that is the plain text. So that's a pretty serious flaw. And that's why there were a whole series of RC4 attacks, more and more and more awful, until they finally had one called No More, which I think is the last one, and they finally decided, better just give it up. RC4, and now everybody's been upgrading all their Cipher suites to get rid of the RC4 for the last 5 or 7 years, because we all realized it's pretty bad. This is the point. You could attack with 4,000 requests per second, you run it for 75 hours, and then you can totally extract an encrypted cookie without knowing the key. So that was one of the many attacks that persuaded people to believe that they had to knock off RC4. So a new improved one is Salsa 20. This is a counter-based cipher and considered quite good. So you have 512-bit blocks of plain text and a counter increments for each block, and each block is encrypted with a key and a nonce and a counter. And you add the original secret state to the output. I'm not quite sure about that part. XOR that with the plain text. So again, it's a stream cipher. You're just XORing plain text with this bits here, but it's considered very good, the Salsa 20. It uses this thing called a quarter round function. So you take your 128 bits and you break it into 4 32-bit words, and then you combine new values for those words by combining it with these equations. And these are left shifts. Left shift by different number of bits, this calculation, and then XOR it with something to get there. So it's just a way of combining these bits to make new values for the internal state. And so then you make, this is your 512-bit state. You have the 8 keywords here, K1 and K2 and so on. You have 2 nonce words. Should be N, I don't see them, but they're in there somewhere. And then 2 counter words, C0 and C1, and 4 fixed constant words. Those are the constants. Nu must be the nonce, and T is probably the counter words. Anyway, that's what you do. This is the state. The state is these 512 bits, and then you go through a series of transformations called quarter round to scramble it, kind of like AES, which had a very similar 4x4 grid, and you'd mix it this way and mix it that way. And so they have pictures of the transformations, how it moves these objects around to scramble them. And so it's considered very good. It has 20 rounds. Remember, AES has 10 rounds, and it does very similar transformations. There's a variant to be faster with only 12 rounds, and versions with 8 rounds have been attacked. So they've been able to find ways to attack it faster than brute force for 8 rounds, but not anything higher. So you have a measure of your security, of your level of security. 8 is not secure, but you have at least 4 more rounds and at least 12 more rounds, depending on which version you use. So it's considered, again, very good. One of the modern ones people should be using. So, as mentioned before, one of the major flaws you can make is use the same nonce twice. If you do, it's very bad. Since you're just using an XOR transformation to mix with the ciphertext. If the same nonce is used twice, then you have the XOR is such a simple operation that you can compare the two ciphertexts together to extract plain text. So that's bad, just like it was in the two-time pad project. There's a underhanded cryptography contest, underhanded coding contest, where you make code that has a subtle bug. And here was code for RC4, and it had a flaw that it occasionally set an internal state byte to 0, so it slowly destroys the state and just stops encrypting entirely. Everything just falls to 0. It's possible for you to make errors in coding it, as an example. And then there's the problem of export ciphers, you mentioned before. Once you force some people to manufacture equipment using deliberately weak ciphers, now they're out there, and in order to interoperate with them, all your old equipment has to have a downgrade to that, and that's a problem. So this is the export grade ciphers are like poison in the water. They foul up the whole network. So let's try another Kahoot. See if I can get past this garbage. 5B. You can change the music. There's about 10 options. They change it on holidays. All right, well, I guess we got here everybody that's coming. All right, so what system puts a nonce value in the key? That's WEP. WEP took the first 24 bits of the key and called it a nonce, which is a pretty bad move. Which one uses quarter round functions? All right, that's salsa 20. All right. Which one has a session key which protects cookies? That's TLS. Good. All right. And which one has 12 or 20 rounds of calculation? That's salsa 20. Good. All right. All right, that's a real name, I think. And Greg. good. All right. Good, so I got the winners. Let me stop this recording.